Alright, it's time to blow your mind. Today we're going to find out what would happen if a solar flare just hit Earth. You might think nothing. After all, we have satellites up there that get hit by solar flares all the time. They're designed to take it. But what about our power grid system, or our telecommunications? Can they handle it? Let's find out. Here's a quick disclaimer. While this experiment is going to simulate some effects of a solar storm, it definitely isn't going to be strong enough to show things like magnetic field reversals or damage to infrastructure. In fact, it won't even be enough to show most of the effects on the upper layers of our atmosphere, where most of the action happens. Our goal today is to show the effect that a solar storm can have on our electronics and communications. So let's get started. First, we need a solar flare. And since we don't have one of those lying around, we'll have to make one. Fortunately for us, the sun tends to throw these things at us all the time. This video is just one example of a coronal mass ejection that the sun threw at us back in 2012. Notice how much energy is in this blast wave as it hits our planet. We're going to try and capture a little bit of that energy in our own flare here. To do that, we're going to wrap a compass in some foil, poke a couple of holes in it, and then place it near some electronics. Here's why. A solar flare is really just an intense burst of radiation coming from the sun. That radiation carries electric and magnetic fields with it, and when it hits the Earth, induces electric currents in the ground and in the ionosphere. It's these currents that cause the problems that we associate with geomagnetic storms, not the magnetic fields themselves. The magnetic fields are what compasses measure, and we know from the video that the magnetic field lines from a solar flare will mostly pass right through the Earth. We want to simulate the effect that the induced electric currents have on a compass, so we can make sure that our instruments can handle a real solar storm. Alright, let's see what's happening here. Notice that the compass needle isn't perfectly straight. It's deflected slightly towards the light. Of course, this isn't anywhere near the amount of current that we actually see during a solar storm. But it does show us that the energy from the flare is affecting our local magnetic field. If this was a real storm, we would expect to see all sorts of magnetic disturbances at this scale. For example, you might notice that the compass isn't just deflected by the light from the flare itself, but also by the light coming from behind the flare. That's because the flare is inducing currents not just in the ground, but also in the upper atmosphere and the ionosphere. These currents form electric circuits between the ground and the ionosphere, and they can persist for hours or even days. As long as the current flows, the magnetic field will be disturbed. If we were to plot the magnetic field strength as a function of distance from the center of the flare, we would expect to see something that looks like this. Notice that the magnetic field strength drops off faster than 1/r, which is the case for a point source of radiation. This means that the total magnetic flux passing through any closed surface surrounding the flare is proportional to the strength of the flare. This means that if the flare is twice as strong, we'll expect twice as much magnetic flux to pass through our surface, and thus twice as much current will flow in the ground and the ionosphere. And since the compass measures magnetic flux, we would expect it to deflect twice as far if the flare was twice as strong. So the strength of our simulated solar storm is directly proportional to how far we can get the compass to deflect. This is great news for us. It means that we can use a simple compass to get quantitative data about the strength of various levels of solar storms. Now, of course, there's no way we could ever simulate a major solar storm like this one here. This storm had an impact parameter of 18, which means that the total magnetic flux it deposited into the Earth. This magnetic field was 18 times larger than the Earth's magnetic field could support. Such an event only happens once every few 100,000 years. But we can still test our equipment against smaller storms. For example, we could look at the 21st of February 2021 storm. This storm only had an impact parameter of 10 to 40. But that's still significant enough to cause damage to our electrical and communications systems. I found a great website maintained by NOAA that lists all of the major impacts from solar storms that have hit the Earth since the year 2000. What I really like about this site is that it lists both the impact parameter and the DST, or disturbance storm time. The DST is a measure of the strength of the magnetic field fluctuations caused by the storm. Both of these numbers are useful for characterizing the strength of a solar storm. So now we know what kind of storms we can safely simulate in the lab. Let's play with our flare a little bit. What would happen if we made it bigger? Well, it's pretty simple, actually. The bigger the flare, the more energy it has, and the stronger the resulting storm will be. There's really not much else to it. The only limit is how much energy the sun can actually throw at us in a given time frame. Fortunately for us, the sun doesn't just throw tantrums all day. Most of the time it behaves itself and only throws out small flares that cause minor magnetic disturbances. Once in a while, though, it seems to go supernova for a few days and pummels us with high-impact parameter storms. Since we have plenty of room on this table, let us go big and simulate an impact. Parameter of 10 to 40. Remember that the strength of our simulated storm is directly proportional to how far we can get the compass to deflect. So we'll need to increase our flare size accordingly. Let's see what happens. Wow, look at that. The needle is nearly horizontal. This would be a pretty serious storm, but it wouldn't be the worst one that we could simulate. With a little more room on the table, we could simulate an impact parameter of 100 to 150, which would be bad enough to disrupt our telecommunications network and power grid. In reality, the effects of a storm this big would probably be felt worldwide, and there would likely be widespread blackouts and telecommunications outages. But again, it's really just a matter of scaling up our simulation. Let's look at another example. What if we turn our lights off and simulate a major solar storm? Whoa, the compass needle is almost pointing straight down. We just simulated a major disaster. Of course, the good news is that the sun doesn't usually throw tantrums this big. Most of the time it keeps its energy in check and only gives us small solar flares. But once in a while it takes things too far, and we end up with major telecommunications and power outages. These events are rare, but they do happen, and we should always be prepared. I hope you enjoyed our little solar storm simulation. The truth is, the sun's storms may be invisible, but their effects are real. Now it's time for a little brain teaser. Here's a riddle for you. I come from 150 million kilometers away, but I still mess with your Wi-Fi. What am I? Take a moment to comment your answer below. While you're thinking about it, don't forget to subscribe. We have a ton of other space weather-related videos that I think you'll enjoy. All right, are you ready for the answer? Here it is. It's a solar flare. Thanks for watching. See you next time.